Hello, my name is Ben and thank you for tuning in. In today's lecture we are going to discuss complex analysis and our topic is mappings. So maybe to start us off, consider the function y is equal to f of x, which is real valued. So we know that this function can be represented or expressed as a curve in the plane. And similarly, if we have a function, say, of two variables, x and y, then these two can be represented by a surface in the three-dimensional space. So now I want to think of a similar way of representing complex valued function. So suppose we have a function w is equal to f of z, then this z is a function of x and y because z is equal to x plus iy, and this function w we've seen before is expressible in the form u of xy plus I v of xy. And so once again we have two variables for the w. So now in order to represent this graphically, if we are to follow the same procedure, then we need a four-dimensional space. We need two dimensions for the independent variable and two other dimensions for the independent variable. So what is normally done, instead of this representation, we normally think of having two planes, one called the z plane and another one called the w plane. And so the function f is represented on the z plane and the image w is represented in the w plane. And so we say that a mapping has been defined from the z plane to the w plane. So as an example, let us see how to find the image of vertical lines and horizontal lines under this exponential map. And so the solution, we know that, or rather this is a function we've been given, that f of z is equal to e to the z, but since z is equal to x plus iy, this is the same as e to the power of x plus iy, which again by properties of elementary functions is e to the x, e to the iy. And so we want to get the transformation function, so we can compare this by maybe this expression rho e to the power of I say omega. And so the transition functions are rho is equal to e to the x and omega is equal to 1. And so for vertical lines, so we have lines in this form. So as you can see, we have some x value and then the y value will vary along the line. And so a typical element in on this line, say that, will be of the form, say, a and some value of y, that is if this point is a. And so with that, the transition functions become e is equal to, rho is equal to the exponential of a and omega is equal to y. And so if we are in the w plane, this is what we're going to do. And so this image corresponds to some movement counterclockwise around a circle as z moves up this line. So as z goes up this line, we'll have the movement counterclockwise around some circle, and of course the radius of our circle is e to the n, and then the argument is that omega, that constant y. And so let's also look at horizontal lines. So once again, with the same transition functions, a typical element on this line will be, so if I use B as this point, so a typical element will be of the form x comma b. And so in this case, our transformation functions become rho is equal to e to the power of x, and omega is equal to b. And so there we have some kind of a constant angle, and then we also have e to the x as the varying radius. So the radius will keep on varying along this ray as z moves to the right. So the image of horizontal line is a ray, actually outward ray, as z moves to the right. So now here we said that the image is, so the image moves counterclockwise, as z moves up the line. So for another example, let us find the image of circles centered at the origin and lines parallel to the axis under the transformation given by w is equal to 1 over z. So for the solution, first of all, we need to get the transformation equations. So we are given that w is equal to 1 over z, which you can think of as u plus iv, and this u plus iv is nothing but 1 over x plus iy. So w is equal to u plus iv, and of course z can be expressed as x plus iy. So with this, we need to simplify. We need to find the real and imaginary parts, because u corresponds to the real part, v to the imaginary part. So this, when simplified, should give us x over x squared plus y squared plus minus y over x squared plus y squared. So therefore our transformation equations are u of xy is equal to x squared plus y squared, and v of xy is equal to minus y over x squared plus y squared. And so let us see what happens when we have circle centered at origin. The equation of a circle centered at the origin is x squared plus y squared is equal to r squared. But we know that if you want to move to polar form, then we have that x is the same as r the cosine of theta, and y is the same as r sine of theta. Of course, remember that x plus iy is equal to r cosine of theta plus I the sine of theta, and so we can have x as r cosine theta and y as r the sine of theta. Okay, and so that then means that u will be equal to x, which is r the cosine of theta, over x squared plus y squared, and that is r squared. And so u is the same as the cosine of theta over r. Now v is the same as r, the sine of theta, over x squared plus y squared, which is r squared, and that means that v is equal to the sine of theta over r. So now next we may need to eliminate the thetas so that we have the expression of v in terms of r. So we can proceed as follows, that u squared plus v squared will be the same as the square of the cosine of theta, or today is the cosine of theta, and I beg your pardon, this should be negative because this is minus y, so this is negative. So this is cosine of theta over r squared plus negative the sine of theta over r, the whole quantity squared, and so this gives cosine squared of theta plus sine squared of theta, this over r squared if you simplify. And so the numerator is 1, so that ultimately we have u squared plus v squared is equal to 1 over r squared. And so once again, this is a circle centered at the origin, so we can say that circles centered at the origin are mapped to circles centered at origin mapped to circles centered at the origin. Now again, an interesting thing to note here is that when r is 1, then the unit circle in the z plane, so circle centered at the origin, in the z plane, are mapped to circle centered at the origin in the w plane. Fine. So if the radius of our circle is 1, then we realize that the unit circle in the z plane is mapped onto the unit circle in the w plane. And maybe something interesting that maybe you can also easily see is that the points that are outside the circle, suppose we take r to be greater than 1, then if r is greater than 1, then we are talking about points that are outside the unit circle. So points outside the unit circle in the z plane will be mapped to points inside the unit circle in the w plane. And now if you talk about points which are strictly less or equal to 1, so suppose we take the inequality less or equal to 1, so that we have a disk, then now point in the disk or inside the unit disk will be mapped to the points outside the unit disk in the w plane. And now for the lines that are parallel to the axis, we'll have two cases, but I'll look at the first case and you can figure out the second case. So let's look at lines parallel to the real axis. And so these are lines of this form. So this is the real axis, so lines parallel to the real axis look something like this. So now in this case, we'll have lines of the form y is equal to b. And so remember our transformation equations were u is equal to x over x squared plus y squared, and v is equal to minus y over x squared plus y squared. And so if we apply these to our transformation equations, we'll get u to be equal to x over x squared plus b squared, and v to be equal to minus b over x squared plus y squared. And so if we take u squared plus v squared, what we'll get is x squared over x squared plus b squared, and this whole quantity squared, plus minus b squared, which now becomes b squared over x squared plus y squared, and the whole quantity squared. Okay, so this on the right hand side will give us, if we add, the denominators are the same, so this is x squared plus b squared, and this is over x squared plus b squared, and the whole quantity is squared. And so with this expression, u squared plus v squared is equal to x squared plus b squared over x squared plus b squared, the whole quantity squared. Now this can be written as 1 over x squared plus b squared. And so the expression is similar to this, except that we have divided this by, or rather we multiply, if you multiply this by negative 1 over b, then you see we end up with that, sorry, this should be b squared. So if you multiply this expression by negative 1 over b, then we get this. So then this is same as u squared plus v squared, same as negative v over b. And so we can write this as u squared plus v squared plus v over b is equal to 0. So now, in order to complete our argument, we have u squared plus, so I want to complete the square with this, so I'll have v plus a half the coefficient of this squared, but then I need to subtract the same thing, and so this is equal to 0. So this means that I have u squared plus v minus 1 over 2b squared. So if I square this, I'm going to get 1 over 4b squared, and if I add 1 over 4b squared on both sides, I'll have 0 on this side and 1 over 4b squared. And so if we compare this expression with the standard equation of a circle, so we realize that this is a circle which is centered at 0, 1 over 2b, and whose radius is 1 over 2b. So in other words, the image is a circle on the W plane which passes through the origin, but having its center on the imaginary axis. And so the image is a circle in the W plane passing through the origin and whose center lie on the imaginary axis. So now I'll leave it for you to look at the image of those lines that are parallel to the imaginary axis, in other words, the vertical lines. And so that's all that I wanted us to look at today. So have a wonderful time and keep safe.